Okay, folks, this is the last lecture of our first little section here, introducing geography and some basic geographic concepts. So today, I'm going to be getting into is the sun, and not just the sun, more importantly, because this isn't an astronomy class, we're not just studying space to study space. We want to see what's in it for us, right? As Earthlings, we are going to be selfish about it. So it's the sun and how it affects life here on the planet Earth. So we'll talk about the solar system, get into some basics there, and then I'll spend a good chunk of the time talking about both solar radiation, the radiant energy that's coming from the sun, and then that'll lead into this discussion of seasonality, the seasons on the Earth. Why do we have warm summers and cold winters and all of that stuff? So we'll get into the mechanics of that and how that works, right? That's the goal. But to start with, one thing I think is incredibly important in any discussion of the sun is this right here. And to say, just look at this image, and I'm going to say, no, 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 this is not okay. Mr. Happy Sun, that's ridiculous. That's nonsense. That's propaganda. I don't even know where this comes from. The Happy Sun thing is garbage. Complete garbage. You know what I see here? Not a friend. I see somebody who lets you down, right? Who's just a big disappointment, even if he does mean well. Now this is the sun right here, right? A big ball of death in the sky. We don't have a happy sun. We have an angry, vengeful sun, and that's great. That's what we want. Having this kind of sun, this works for us. This keeps us alive on this planet because this sun is constantly burning and just sending out this radiant energy, and we're able to get some of that, and we're able to survive. Okay? Again, this guy, he's like, I'm too sleepy to shine, and then we all die. That's garbage. This is the good stuff right here. And I'll point out, too, not only is it a big ball of death, but it's a constant ball of death, meaning that it's not heating up and cooling down and all of that stuff. Doesn't have its hot days and cold days or whatever. And this will become important as we get into climate change in the next section of the class when we start discussing that, because that's one. I don't even want to call it a hypothesis because it doesn't come from a good, curious place. But some people have said, look, the reason why temperature is going up is because the sun's just burning a little hotter and it'll cool down and then we'll be fine. That's nonsense. No, and that's the thing with the sun. That's what's so great about it is it's constant, right? It's solid for us. We can count on it to keep doing the same thing that it's doing. And sure, like in, I don't know, there's like 1 billion years, it's gonna like swell up and then implode and wipe out our solar system or whatever. So it's got that. It's a little crazy, but we're not going to be around, right? So who cares? Right? If humans get to that point, like you're still alive, well, yeah, hopefully we can move someplace else. But it ain't me who has to move. It ain't going to be you. So we're going to be dead. So who cares? We're just going to go with it. All right. So just keep that in mind. The sun, constant ball of death, and really unbelievably important to everything that we're going to be talking about from here on out. And not sometimes I'll point that out explicitly. Other times I'll just kind of, it'll just be assumed it'll be there. But really everything, every system, every process, everything I get into for throughout the rest of the class, it's connected to the sun in some way. Either through, processes like photosynthesis, chemical reactions that are connected to temperature change, just the gravitational pull of the sun that keeps us in this position, all sorts of different stuff. It's all connected to the sun. So that's why we're going to spend time with this now. All right, now to start with, and how the sun works, and don't stress over this stuff. And I'm going to give, in this first little chunk here, I'm going to be giving some statistics, different, numbers and concepts and all that. Don't stress over it. I'll point out any numbers I really want you to commit to memory, or I really want you to understand. Same thing with like this concept of solar fusion. Don't worry about it. All the whole hydrogen atoms. We're not a chemistry class. Blah. You get excited by this? Go read a Wikipedia page or whatever. The idea here, I want you to know, is that the sun works in this very specific way, and this is why it is the sun. This is why it is so useful. It's this fusion, this release of energy. It's plentiful and it's continuing to, happen every day of our lives. And this is why the sun is this useful thing. All right. And we would love to figure out how to replicate fusion in this way. Right? If we could do what the sun is doing, because that we understand the concept, and that these hydrogen atoms are smashed together and it's releasing subatomic particles, and then energy is also released in the process, and blah, 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 blah. We get the concept. We just can't do it, right? That practical application. We have yet to be able to successfully do it. The closest we've come is this right here, the hydrogen bomb. So we can use it for evil. We can use it to blow stuff up real good, but we haven't figured out how to, use it in a way that it just produces clean, renewable energy. That's the end goal. And the hydrogen bomb, I mean, this thing is crazy in the sense that we build the thing, we blow one of them up, and all the army guys go, "Whoa, that's psychotic. We're not going to use those anymore." So we get rid of the hydrogen bomb and we switch to the nicer nuclear bombs. Right? That's the friendlier, nicer way to kill people. So we use it for evil. Can't use it for good, but we're constantly working on trying to figure this out. A few years ago, I remember a story of a physicist got a little bit closer to it, but it means we'll be able to do it in like 400 years as opposed to 500 years or something like that. It's in the far off future, but people are still working toward it, right? But, fortunately for us, the sun knows how to do this, and it's doing it, and it's working for us, and that's what's powering our solar system. Now, what we should do in discussing this is get into the geography of the sun, of our solar system, of everything. So we've got a few terms here that we're getting into. Number one, when we say the universe, we're talking about everything that exists, right? This massive, massive universe encompasses everything. And then within the universe, we have multiple galaxies. Right? We ourselves exist in the Milky Way galaxy. It's not the only galaxy that's out there, but it's ours. Okay? We're in there, and it's made up of roughly 400 billion stars. Okay? So our sun is one of these 400 billion stars. And this image here, and I do love it. You've got the label. You see our sun right there, of course, because it's got the label. Somebody probably just wrote that on there anyway, like we're going to check. Like you can see your house or whatever from here, right? But you can see that our galaxy is this massive thing. And of course, what's crazy is it's not the only one. In fact, looking at this image here, this is from the Hubble telescope. What are these bright lights and things that you see here out in the universe? And what you probably do is, and this is what happens whenever I ask this question in a classroom. It's like, what are these lights? And everybody just goes, galaxies, with no interest. Like the same as saying like, telephone, shoelace, like just whatever, just saying a word. These are galaxies. My God, that's amazing, right? Because if you look at it, We got 400 billion stars here, and 400 billion stars here, and 400 billion stars here, and so on. And what's really great is this is a cropped image, right? It's not like the universe is just this rectangle that exists out there, and this is the edge of it. No, it just keeps going, right? Massive, humongous thing out there full of these galaxies. And so our galaxy is one of many out there. And our solar system is the term we use for the sun and all the objects that are kept around it, right? So our planet, our moon, as well as the other planets and moons and stuff that are out there, Jupiter and Neptune and all that stuff. That's our solar system. We are one tiny, tiny component of our galaxy, which is a tiny component of the universe. And even the Earth itself, tiny little component of our solar system, right? How tiny and insignificant are we? Isn't that great? And this is what you learn in this class and as you start to study this stuff. Like we go back to the geodesy stuff and getting into like, no, the Earth, it's actually not a perfectly round sphere. It's actually a lumpy potato. And you learn here that, oh, actually, no, you're not special. You're tiny and insignificant. It's a real blow to the ego when everybody around you has always been telling you like, oh, you're special. Like your high school counselor or whatever, saying, you're a special little flower. No, you're pretty tiny. Yeah. Are you processing that? Are you feeling depressed? Don't actually. I don't understand that actually. The idea that in learning that we're not the only planet or whatever, that we're not special and it makes life bleak and depressing and all that nonsense. If anything, I think everything is better once you know this for a few reasons. Number one, you're actually I think we're more special, more unique, more fantastic in the sense that out of all these other, solar systems, galaxies, all this stuff in this gigantic universe, we're unique, right? There's nothing else out there. I mean, you hear from like NASA folks that they discovered an Earth-like planet, but that doesn't mean we didn't go there and like shake hands with those Earth-like people or whatever. No, it's discovered like an absence of light and stuff looking at telescopes. So we kind of make assumptions and things like that, but no, we have not found anything remotely close to what's happening here. So it's pretty remarkable. And whether you want to say that it's that's there's a religious reason behind that, or whether you want to say it's just kind of chance, it's chemical reactions and things just happening, and this is the result. However you want to frame that or make sense of it, it's still pretty fantastic, right? That we are unique in that sense. So think of it that way. Don't get fully depressed at this moment in time. And another great thing, as we'll see, is that in being so small and tiny and having this massive, massive universe around us, we're able to learn a lot about who we are and how we came to be. And a great example of this is our theory of how the solar system, how our solar system came into being, right? This term planetesimal, right there, it's a concept of like an early planet or a proto-planet. So like the Earth, before it's the Earth as we think of it today, with continents where they are and oceans where they are and forests and glaciers and all that stuff, it's just a big lump of rock, right? So it's the idea of how these initial planets came into being. And so the concept is our suns, like our sun, they condense from a nebula. And a nebula is effectively, it's like pollution out in the universe. It's dust, it's gas, it's a cloud of stuff out there, which again, I know, it doesn't make it sound that sexy. That we sprung forth from pollution. But, hey, we did. You make the most of from where you come. But it's the idea that so the sun condenses, and then as that starts to grow and develop into this massive, massive object, it's exerting this gravitational pull. And so that's pulling all this other dust and debris and stuff around it. And so little bits of material smash into other little bits of material and they start to stick together and build up. And we get bigger hunks of material and debris and all that until everything gets bigger and bigger and bigger. And we start to get these planetesimals. And that's the idea here, right? So it's stuff smashing together all because of this gravitational pull. And it's at this point it's worth getting into. We're not going to dwell on the real mechanics behind all this stuff, but when we're talking about gravity, it's worth getting into the fact that what we're talking about here is not simply that if I hold something up and I let go, it falls. Like that's what we tend to think of. We're talking about gravity, but really it's this force, okay, this attracting force that all objects exert. We all have like this gravitational pull just because we have mass. We're very tiny, so ours is meaningless. It doesn't really matter. But the Earth, being as big as it exerts this larger gravitational pull, and so it's pulling us toward it, toward the center of the planet. So that's why we're stuck here, right? We're attracted to the planet or pulled toward the planet because of that gravitational force. The moon, our moon is, it's big, but not as big as the Earth. So it's pulled toward us, it's kept around us. That's why we see it in the sky. And then the sun, of course, the most massive thing in our solar system, is keeping us close to it, as well as the other planets and all that stuff. All right, so that's what gravity is. It's this attracting force, and we'll continue to talk about it. But that's the idea here with this whole planetesimal theory that we have. That sun starts to form. It's exerting this gravitational pull. That's why all this dust and debris is moving around it. These things start to smash together, and of course, you get with a lot of this stuff where we don't have photographs of it or whatever. You get a lot of paintings or commissioned by like NASA folks to try to give you a sense of what was going on. And some of this stuff, it always cracks me up because it looks like we should be playing some Pink Floyd right now and just like getting mellow and all that and looking at the solar system and how it's starting to form. But no, it's not this cool. It's this violent, nasty, horrible thing, right? You gotta keep that in mind. That when it comes to nature, quite often, whether it's here on the planet or it's stuff happening out in the solar system or whatever, there's a lot of violence. There's a lot of scary, ugly, awful stuff. But from that, we get the cool stuff. Right? So, we want to keep that in mind. We don't have a happy sun, we have an angry sun with our planetesimal stuff forming here. It wasn't this mellow, groovy kind of experience. It was ugly and it was violent and it was awful. And we'll talk later about what the planet would have looked like, in the early initial days. This was 4.6 billion years ago is when our planet forms. And it definitely did not look like it does today. And I'll get into the details of that later. I think, in fact, the next lecture in the next section, we'll start talking about that. All right, but this is how our solar system forms. And your question you should be asking, my good little critical thinkers, is, that sounds cool, but how do we know? Right? Because by definition, we couldn't be here. We didn't have humans hanging out watching this stuff because our planet didn't even form yet. Humans won't exist until much, much later in time, right? This is happening 4.6 billion years ago. We don't really show up Homo sapiens until over 200,000 years ago. Big gap right there, right? So how do we know? Well, this gets back to our really cool situation in that we're this tiny, little, insignificant group of folks on this tiny little insignificant planet in a much larger universe. What we've been able to do is look out into space, look out into the Milky Way, and we've been able to observe this phenomenon happening in other parts of the galaxy. So we've seen solar systems form, right? And in doing so, we start to notice these patterns. That if we see this same planetesimal theory, story happening in this part of the galaxy and that part of the galaxy and over here, and we're not seeing anything else to suggest that planets and solar systems form in any other way, well, then logically, we can apply that to our specific situation here, right? It's that deductive reasoning, if you want to think about it. If we have this general knowledge that is being formed by these other things out there, we can apply that to our own situation. All right, and we'll get more into that when I get into the geology discussion in the third section of this class. We'll talk more about just this idea of how we're able to draw conclusions, how we can say we know something even if we weren't there at the time, even if we don't have like that direct visual evidence or something along those lines. And a lot of times, students and skeptics of science will hear this stuff and they'll go like, oh, okay, so you don't actually know what happened here, you just seen it someplace else. I don't buy it. But really, when you think about it, we live our lives like this. We base decisions and we hold truths and stuff like that in our minds based off of way less evidence than we have for stuff like this, right? So keep that open mind. And in the upcoming weeks, I'll be spending some time talking about them, how we know what we know about what took place billions of years ago, or what's, taking place deep in the universe or whatever. Okay, that's the concept there. But for now, we're just going to depart from here and get into modern day and get into what the sun is and what it's doing and why we care about it. So again, here are some of these statistics, these numbers that are cool. I include them because they're cool. I'm not going to test you on this stuff because honestly, like that's high school kind of stuff, right? Having you memorize a fact and belch it out onto the test paper or whatever. No, we're going to get into concepts on your exam, the why stuff is happening or what that means. So I'm not going to make you memorize this exact stuff, but it is kind of cool to see that like the sun itself, it's like 98.5% of the solar system's mass. Right? So out of all that stuff that was in that original nebula that, came together and formed, 98.5% of it went to the sun. And so that means the remaining 1.5% not only went to us here, but all the other planets and planet-like things and all that stuff, and the moons and all of that. So again, you can see how tiny our planet is in comparison to the sun. And you can also see how hot it is here, 11,000 degrees Fahrenheit. That's ridiculous. But unfortunately, we're far enough away, so we're not going to melt. Well, we can exist. And the sun, what it's doing is it's sending out two things. It emits two different things that are of relevance here. Primarily what we care about is solar energy, right? This radiant energy that leaves the sun, but it also emits solar wind. And I'll talk about that briefly as well, what that is. But these are the two things that the sun is sending out at every moment of every day, right? And heading out in every direction into the solar system. So this first thing, energy, radiant energy, what we're talking about with radiant energy is that it moves through waves. That's how this energy travels. Okay? And depending on the wavelength, which I think, do I have on the next? Let's move on to this one. With wavelength, what we're talking about here is just how far it is between one crest of one wave to the next crest of the next wave, right? So you can see it here. So we describe things as being long wave if they have a relatively longer distance between these waves compared to short wave where it's, more stuff packed together. And this whole, long wave and short wave stuff, if I go back here, helps to explain the different types of energy along this electromagnetic spectrum. So we tend to think, like, when we talk about the sun, we're talking about just sunshine or sunlight or whatever. Visible light is one form of this radiant energy with one specific wavelength, but we have other stuff. And we'll talk more about the other stuff in the next section. Things like, ultraviolet radiation, those UV rays, the stuff that gives us sunburns and suntans and things like that. That's another form of solar energy. It's just a different wavelength, right? There's also other, even nastier things, X-rays and gamma rays and stuff that would just, riddle us with horrible, cancer and all. We could not survive if we kept getting blasted with all this stuff. Fortunately, our atmosphere is doing a lot of work to keep that out of here, to keep it so it doesn't come down to the surface, so we're able to exist. So we'll talk more about some of this different radiation later, but just for now, be aware. This is what the sun, we're talking about solar energy, this is what's coming our way, right? These different types of waves. And really, to start with, what we can get into, and this will be developed more, I'm going to spend more time on this later on when we get into climate change, but the general idea is the sun is sending to us the shortwave energy, and then we're getting it, but we're not keeping it, right? We don't keep all of this energy, because if we did, we would just, explode. We can't just keep, receiving all of this energy and just hold on to it. We can't store it in that way. It'd be too much. So we use it. And when I say we, I mean, it can be us humans ourselves, or it can be other objects and things that just exist on the planet, right? But it's used, it's absorbed in different ways by different things. It's used for life on this planet, right? Or just other chemical processes or things that are taking place. And then once it's been used, it eventually heads back out into space. So everything we're taking in, eventually we're getting rid of it, right? And it's transformed into long wave energy, and that heads back out into space. And this will become, this whole short wave, long wave thing will become more important when we get into the greenhouse effect, and the thing that is leading to global warming, which is leading to greater climate change around the planet. So this is a key thing for understanding how all of that climate change stuff works. But again, that stuff we'll be talking about in the future, in the next few weeks here. Okay? But just keep that in mind for now. Now, one term that we will use here that is useful is insolation. And it's an abbreviation for incoming solar radiation. Okay? And this is really, this is sciencey talk, really, is what it is. Because we don't want to talk about sunshine or sunlight or whatever, because that doesn't sound sciencey. And it's not correct. It's not all encompassing. All right? So the term we're using is insolation to describe that visible light, but also the UV stuff, and all of these different wavelengths that we have, right? So whenever I say insolation in this lecture and future ones, we're talking about, you can think of it as sunshine, but just keep in mind, it's all of that radiant energy that's coming to the Earth. All right, so I just want to make sure that's clear. And as this insolation is heading down, it's important to realize too that not all of it is even absorbed. So like as I just said, it comes down, we use it, it gets converted to long wave stuff, it heads back out into space and all that. But some of it, roughly, it's like 30% of it, gets immediately reflected right back out into space. And that's another way of us keeping cool and not getting too hot. It's through this process we call albedo. Okay? And you can see it up here written ALBEDO. Albedo is this, it's the reflective quality of some body or surface or whatever. And it's all based on the color of that object, right? It's the general idea that the darker the color, the more solar energy is absorbed and the less is reflected. Right? The lighter the color, the more stuff is reflected. All right, so like we have in this example here, fresh snow, 80 to 95%. Okay, its albedo is 80 to 95%. That's how we describe it, meaning that of all of that insolation that hits that fresh snow, it's going to reflect anywhere from 80 to 95%, and therefore, absorb 20 to 5% of that stuff. Whereas asphalt it has that albedo of 5% to 10%, meaning it's only reflecting 5 to 10% of it, and it's absorbing, 95 to 90%. Right? And we experience that like walking around the Antelope Valley in the summer. You head out into a parking lot, after you go into, the air conditioned store and you come out and you walk toward a parking lot and you can see the heat wave lines coming off of it. I mean, it's just so hot. It's because it's absorbing that energy, right? Whereas, stuff that is lighter in color, it's going to reflect more. That's the general idea. And here, look, I was close enough. Earth's average albedo, 31%. All right, so that's a key thing. Again, we'll be talking more about when it comes to climate change and just staying cool on this planet. But at least it's an introduction to this stuff for you guys. All right, but that other stuff that we're not just immediately getting rid of, that remaining 70% of solar energy, that's quite useful. It's very important for life on this planet. And what this is another statistic you don't need to know, but it's something that I do find fascinating here. We receive 28,000 times the amount of solar energy than we humans consume. All right, which just is a mind-blowing thing. All this energy that we're not putting to use here. In this map, it might be kind of hard to see, but maybe you can make it out. Like here's Florida right there. There's California over here. Going down into Mexico. Here's South America. You guys follow that, and Africa, and so on, right? And so what it's showing, the lighter the color, it shows the better potential for utilizing solar energy, right? So the real light yellows, and then the darker the color, getting into those dark reds, solar isn't quite as efficient, right? Because of cloud cover or whatever it might be. And so what this really shows us is where places would be, it would make sense to utilize solar energy, and we here in California are definitely one of these places, right? It makes sense for us to use solar energy. You guys all have, all of my students, let's do this. You guys all have the solar panels on your roof, right? Right? No? Some of you do. I've done the polling of my classes in the past. And of course, most students at AVC, at least out of the classes I've spoken to, most don't have solar panels up on the rooftops, right? And a lot of people will say, like, what are you, what? Oh, it's free energy, man. It's like, why wouldn't you do it, right? You just get the sun is turning on your lights. I mean, that just makes perfect sense. And you get to care about the earth. What, you don't care about the earth if you don't have them? And of course, no, that's not the case. It's not free energy, first off, right? Because how much does it cost to put these things up? It's like 20 grand, roughly, to get a system that's going to power a house. That's a huge amount of money. And we've had, tax incentives and stuff to try to make that easier for people, but still, for most folks, you don't have to, or you don't have the ability to just like, well, I got this $20,000 just lying around. Let's use it for solar panels. Like that's what I can use it. No, usually it's paying off credit cards or medical debt or whatever, even if you get that kind of money. So of course, a lot of people can't do it, or you have to go into some kind of leasing agreement with some kind of company. And there's a lot of scam stuff and creepy companies, starting about 10 years ago when this really was getting underway here, this whole consumer rooftop solar panel stuff. So just right there, it's expensive as hell. And that also doesn't get into the fact that you have to own your home, right? You can't, typically go to a landlord and say, like, would you mind investing, 20 grand into this so we can help the earth and all that? No, we don't. That cuts into profit, so we typically don't see that at all. We also, have the case if you're in an apartment too. Like that's just assuming we have a single family home. But if you're in one apartment of many in a building, that's another issue. So it seems to make sense. And you hear a lot of, rather out of touch, well-off people who will, go around like, why aren't you people doing this? It just makes such sense. No, there's a big economic thing behind it. And that's something to be aware of. How, capitalism is connected to environmentalism. There's a movie, it's back on YouTube. It was taken off of YouTube, it's back on there. It's called, I think it's Planet of the Humans. It's a documentary, and it was produced by Michael Moore, who has done a bunch of other documentaries. You guys have probably heard about the guy. Maybe have an opinion on the guy. And when I say he produced it, it really means somebody else made it. But see, I don't even know the guy's name who made the movie. But that's why, Michael Moore signed his name onto it so it would get more coverage. But it's all about this Planet of the Humans documentary. It's questioning this whole idea of solar and renewable energy and stuff like that. And a lot of environmentalists aren't happy with it because they feel it's misleading and it's trying to get people to say like, see, so solar's bad, so let's just go back to gas or whatever. I've watched it. I think it's great. Now, whether every single thing is 100% true, I mean, they have all sorts of fact-checking stuff and they're saying it's worth diving in deeper to some of these claims. But what I love about it is they are pointing out that issue, that connection with capitalism and environmentalism, and how it really doesn't work to have that, to have like green capitalism, because ultimately, profit is going to, triumph over saving the earth. That's kind of the idea. So there are a lot of issues we have with solar energy right now. It should be a no-brainer. It should be something we all do, but we don't, for a variety of reasons. And one fascinating thing, too, it's not just, an economics or money thing. We also have stuff like this right here. You guys see this? Can you read these signs? And this is great, too, that I'm not in a classroom, because I usually have to ask, like, does this house belong to any of you? I've had some students who are near this area, but I've yet to teach a student who, helped hang up this sign. But yeah, so what we're looking at here is it's on the west side. Of course, you'll see why when I get into it. But it's in West Palmdale, Quartz Hill area, and it's over by, Hillview Middle School. Okay, and it's because years ago, Hillview, as all this solar stuff was starting out, they decided to put in solar panels, and these panels, fantastic. I mean, it was all in the field. Big columns, these giant steel things, coming out of the field, and these massive panels up on them. And what was cool is that the panels could rotate, right? So as the sun is rising over here, the panel's tilted, so it gets the maximum amount of solar energy, of that insolation at that time of the day. And as the sun goes through its daily arc through the sky, as it gets up, to solar noon, to its highest point, and so on, those panels are going to move with it. So it maximizes that insulation. And as they would move, it would, ensure that the school would get 100% of its energy needs from these solar panels, which is just, for me, as I'm learning about, what they're doing and watching the stuff get built and all that, I think that is so cool, right? From an environmental standpoint, the idea that we don't want to be burning fossil fuels for energy, and that's something we kind of tend to forget or overlook, is that when we are using electricity, we forget that so much of it is connected to burning something, natural gas or diesel or coal or like whatever it might be, right? We don't just generate electricity out of you know good feelings and stuff like that. It's coming from something dirtier, right? So it's great that this school where you have a lot of energy being used to teach kids throughout the day, and it's going to come from a clean, renewable source. But it's also, as a tax-paying citizen, it's also a thing where it's like, great, yeah, let's invest in this stuff now, so that after we pay off this initial stuff, the energy costs are going to be minimal, right? And that way, that money can go to textbooks or field trips or, to the students themselves, to the important stuff, not this, the utilities, right? So it's going to be fantastic. But once these things get built, these signs show up. All right, so this first one on the left: solar panel glare, public safety issue, panels must go. And then on the right, beware of the glare. Yeah, do you know what the glare is? Do you know what the idea was? Can you figure it out? Yeah, it's the idea. What these concerned citizens were saying is that as good people were driving their own children to school, whether to that school or the other ones, like myself, drove my kids to another school not too far from there. And so the concern that these people had was that I was going to be driving along with my precious babies in the car, and these panels would be tilted, and the sunlight would hit it, and then it would bounce back and hit me in the eye. And I, of course, being blinded, would panic and overcorrect with the steering wheel and scream and crash into other cars, and there would just be carnage everywhere. Everywhere! Beware of the glare. Um, there was no glare. Having driven this route, multiple times a day for years, never saw any glare whatsoever. In fact, somewhat ironically, the only glare I ever had to deal with was from one of these houses where they put in some kind of window film or whatever to keep the sun out of their kitchen, and that would bounce back and hit you in the eye, right? But the solar panels, no, they didn't work that way. That was never, ever an issue. And honestly, I mean, come on. Was this whole beware the glare thing, is that really about, it being a public safety issue? No. No, 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 it's not that at all. What is it about? You think about it, and you can see one of the clues is that as I'm taking this picture of these signs, I'm down at the bottom of the hill, pointed up. All right, why do people have these houses right here? Part of it is it's because of the view, right? It was a big selling factor. It's part of the spatial analysis of real estate. If you can be kind of up higher, have a view, overlook things, that's a great deal, right? Now, I find that silly, because really what your view is here is of other very similar looking houses in the area. So I don't, that to me doesn't strike me as a selling point. But for these folks, and I'm mocking these people, not mentioning that I live not too far from these people, and am guilty of many other bourgeois crimes like these folks are. But still, I don't put up signs. But it's the idea that what it is that these solar panels being put into place, it's an aesthetic thing, right? People were upset because it blocked their view, and they were concerned that that was going to hurt their property values. And again, you see this connection between capitalism and environmentalism. Now, to be fair, apparently there was one house that was like right there near the field by these solar panels that, like, when this one solar panel would tilt over in the afternoon, it would actually heat up the house. And so, like, this one house would get to, like, 500 degrees or whatever. And I guess the people complained. Okay, so I get it. Like, that's an actual issue. And I think they fixed it so that one wouldn't tilt all the way, so these people wouldn't bake alive. That's perfectly legitimate. But this beware the glare stuff, nonsense. Nonsense. But get this, they're not there anymore. The panels were taken down a couple of years ago now. And I noticed as I was, again, driving past this area, I see these things getting pulled down. And I go, no, the bastards won, right? We're all bewaring the glare. And so what I did, because this is how I roll, I called up the school, right? I called the school and I'm like, what's the deal with these solar panels? And the woman who I spoke with, she was explaining to me, yes, we're tearing them down. We're going to replace them with other ones. And these other ones, from what she explained, not as efficient, right? Because of all this stuff, not as good. But she finished up explaining this to me, was saying, so the eyesores are gone, thinking that I was a concerned citizen who, lived there and didn't want to have these ugly things. And I didn't even explain to her that, oh, no, quite the opposite. I want the eyesores because I want to have, cleaner energy and stuff like that. But it just amazed me, right? And it's a great lesson into how difficult using solar energy actually is. And so it's something to keep in mind. Energy is something we got to figure out, right? And that's said in a broad way. And some people are relying on, like, look, if we just figure out solar fusion, we're good. We do that and we're set and we can, keep our lights on all the time and it'll be cheap and free and like the world will be this wonderful, wonderful place. It ain't going to happen anytime soon. Okay, so we gotta put that aside. Like, sure, people should keep working on it, but we can't just sit around waiting for that. We gotta figure out what we're gonna do with the stuff we have. And that means developing the technology we have and installing it and using it in a better way. It also means questioning, our need for electricity, what we're using it for. The fact that we just leave lights on all the time because we can, right? You go back, if we were back on campus, if we were in Hazy Hall, you're walking to the classroom to get this stuff, you would walk past all of these stupid lights embedded in the wall that are just constantly on, right? And it's to give it a spaceship vibe. It's a whole deal. The architect was like a Trekkie, and that's why that building looks the way it does and all that. But we got these damn lights that are constantly on. There's no switch. As far as I can tell, there's no way to turn this stuff off. And it's probably like, LED stuff. And people would say, oh, but it's efficient. But the point is, like, yeah, but it doesn't have to be on. Like, whether it's efficient or not. You know what's more efficient? Not having damn wall lights constantly on. Again, but here's my rant for the day ready. So we got to figure this stuff out. All right, just from a human standpoint. But another thing that you students should be thinking about is the fact that solar energy is not going away, or alternative energy as well. Another way to think of it, wind and all this other stuff. And you see, like that movie I talked about, you gotta watch it with, a critical eye, as you should watch anything. But that Planet of the Humans, you can watch it. It gets into issues with wind and solar and some of this, but it doesn't mean necessarily that we need to get rid of this stuff, and we're not going to. I don't see that going away at all. But what we're going to need are smart people who are able to figure this stuff out, to fix this system and to make sure it works for us, right? That's the goal. And so with this, as we're thinking about it, as we're doing this, we're going to need these good people. That's college students right now, right? People who are going to graduate in the next few years. And it also doesn't mean that you have to be an engineer or go into one of these, STEM fields or whatever to design better solar panels. No, actually, we need people who are well versed in the humanities and the social sciences and stuff like that to deal with like the political ramifications of putting in solar panels in a middle school field, right? To deal with the public. Mapping of this stuff is a big deal. And I know a lot of geography students, like, look, I'm not telling you guys you should all switch your majors to geography. I would never do something that tacky. But I just know that, like, all these geography majors that I've kept tabs with, who graduate and they actually get good jobs out of college because they have skills that people need and all that. I know there are, a handful of folks who have left like the program at Northridge and have gone on to work for solar companies, not to develop the solar stuff, but again, to do this spatial analysis and to figure out the more human side of this stuff. So it's a great opportunity. We got to fix it. We got to figure this out. We got to, deal with this whole energy problem that we have, both our love of it here in the United States, the fact that we just kind of assume too that it's free and showing up all the time, and we forget the fact that it's connected to climate change, which again I'll be getting into. So we got to figure out that addiction, but also like how can we improve our energy sources? That's where geographers are going to be really important. But again, I'm not telling you guys what to do. If you want to graduate college and not have an actual job and just be in debt, like, go for it. Nobody can tell you what to do. You're a sovereign citizen. Yeah, but if you actually want to have a future, it's something to look into. Feel free to, shoot me an email if you're curious about any of this stuff. All right, pep talk over, rant over. Let's get into this other thing, this solar wind that I mentioned earlier. So with solar wind, it's another thing that is emitted by the sun. Different from the solar energy, we're dealing with these charged particles that just get belched out from the sun and they head out into space. And luckily, we have an invisible force field that deals with this, right? So these would be nasty. It would be awful. Life wouldn't exist here on this planet in the way that it does anyway. If we constantly had to deal with this, solar wind coming down here to the surface. But we have an invisible force field, which sounds made up. Sounds like something that, a third grader came up with. But no, we do. And it's called the magnetosphere, which is our fancy term for our magnetic field. And we'll get into this later. We'll talk more about it when it comes to like plate tectonic stuff and all that down the road. But the magnetosphere, it's generated in our liquid outer core. Okay, so inside the Earth, we have our solid inner core. It's solid metal, and then around it we have this outer core that's the same metal, iron and nickel, but it's liquid and it's churning around. And as that stuff moves around, it produces this magnetic field that fully encompasses the planet. And so it's like how compasses work, and it's how birds can navigate and stuff like that. But it keeps this solar wind from coming in to the lower reaches of the atmosphere and reaching the surface. Okay, only a little bit is able to sneak through. The worst thing that it does is can screw up radio transmissions. If you're listening to the radio in your car, it'll be a little more staticky when we have more sunspots and more, solar wind activity and stuff on the sun. That's it. It's an inconvenience. And also what's cool is we get these auroras, and I'll show you that in a second. So we get like this free light show too because of it. So here, again, getting back to, like groovy paintings, what this is showing, and of course it's not to scale at all, but it's the idea that we've got the sun, solar wind is coming our way, and this spider looking thing that we have here is our magnetic field, our magnetosphere, and it's deformed. It would be symmetrical, but apparently all of this solar wind that's hitting it deforms it in this way. And so again, only a little bit of that solar wind is able to come in at the poles, at the North Pole and the South Pole. And what that does is it comes into the atmosphere, but up high up, before it even comes down here, it burns up in our upper reaches of the atmosphere. And that process leads to these auroras, or what we call, like in the northern hemisphere, the northern lights, which are these beautiful light shows. And you don't see them down here. We're too far south here in California. But if you're up in Alaska, Canada, sometimes it even comes down a little bit further south than that. But if you're up there at night, you can see these spectacular light shows, and that's that solar wind burning up. It's the Earth, helping us out here, right? The magnetic field making it so life can exist. Right? So we don't even have to worry about that. And so those are the two things. The sun is emitting solar wind, which we don't have to worry about, and then solar energy, that radiant electromagnetic energy that's coming our way, that is incredibly important for, life to exist, as well as for, us to figure out, like in the case of developing solar energy based electricity sources, it's going to be important to our future on the planet. All right, hopefully that's clicking and making sense. Now, I'm going to shift gears a little bit, and we're going to get into our seasons and the seasonality. All right, and now we're also getting to the point where any of these numbers that I have up here, they're important. You need to know them. You need to write them down in your notes. You need to commit them to memory. And they're important because they help to make sense of other stuff. Other things I'm going to talk about in the next few minutes, or things I'll be talking about, a few weeks from now in other lectures and other sections of the class. So from here down, the rest of this lecture, these numbers are important. So just keep that in mind. So to start with, we're going to look in, and this is important for understanding the seasons of the Earth and why it's hot sometimes and why it's cold other times. It's important to just understand like where we are in relation to the sun and how we interact with the sun. Okay? So we revolve around the sun. Okay? We have a revolution, right? That's our path around the sun here, and it's an elliptical one, meaning it's more like an oval than a perfect circle. So this here, in fact, I'm going to do this laser pointer thing. So this right here is our revolutionary path around the sun, this elliptical thing. And we also, while we're cruising around the sun, we're also rotating, okay? And so there are two things at work. Like rotation refers to that spinning around the axis. And unfortunately, if we were in a classroom, I'd be doing this stuff with a globe, and I'd be walking around and spinning stuff, and I have all sorts of props to help this make sense. Just, visualize. I'll try to be as clear as possible. I also have a YouTube video linked in the slideshow later on, and you can find a lot of good animations about this stuff online to further help you grasp it. But I'll do the best I can with just my, the poetry that comes forth here. So rotation means spinning around an axis, right? And remember that axis, it's where that invisible line exits at the North Pole and the South Pole, and it's around that axis that we are spinning, right? That's our rotation. And so we rotate once every 24 hours, right? But we also revolve at the same time around the sun. So revolution doesn't mean spinning. It means that being pulled around because of that gravitational pull, right? And it takes a calendar year for one complete rotation, which we've measured at 365.242 days. Okay? And that 0.242, roughly a quarter, that's ugly. That ruins stuff. So how do we fix that? We have a leap year, right? Every 4 years, we throw in a February 29th, and that's a way to adjust our calendar so it doesn't get all out of whack, right? We see them with a lot of stuff. Same thing, the rotation isn't a perfect 24 hours. We find this is the same thing, like with the geoid. We find a lot of stuff that we assume to be perfect. It's not perfect. It's just, it's so close. But of course, that makes sense. Like perfection, like that's an idea. That's a human idea, right? And our idea of numbers and all that. So like it's a very human thing to just be confused that the universe doesn't work exactly as we expected it to. So we found this stuff. The more we study, the more we learn about these little variations, and we take that into account, right? So it's over 365 days, but still, that's our one complete revolution. And as I said, it's not a perfect circular path. It's this elliptical path that we have, or this oval shape. Now, this image, it's exaggerated for it to make sense here, but it's still the ideas are true, and we have two key dates I want to point out. So we start with right here this perihelion, which takes place on January 3rd, roughly. And you'll find with a lot of these dates, it's always give or take a day, and that gets back to that whole 0.242, the leap day, leap year thing. These things can shift a day or two, depending on what year it is, depending on where we are in that leap year cycle. So just keep that in mind. But typically speaking, like on January 3rd, we have the perihelion, which is the date of the year where we are closer to the sun than any other date. Okay, and so you can see that with this image here. So January, super close to the sun. And you guys, I mean, you expect that, right? Because January around here, we're burning up, right? It's so hot, right? No, it's cold. Come to think of it, my God, it's been so long since I've experienced a January, and being stuck at home with the whole coronavirus thing. I had time. What is time, right? But no, from what I can remember, January cold. That's winter. Oh, that's weird. And then if we continue on through the year, July 4th. Again, give or take a day. It's not always on the 4th of July, but we have the aphelion, which is the date of the year where we're farthest from the sun than at any other point throughout the year, right? So when we are hot as hell, here on this planet, we're actually much farther from the sun at any other time throughout the year. And it's a difference of like 5 million kilometers, which is, huge, but also kind of insignificant with all these numbers here. But still, it's one of those things where I'm looking at this, like, what's going on, right? Why is it like this? And this is a thing, that is kind of a confusing, odd deal that makes people question stuff. And again, I want to stress that it is not a case of the sun heating up or cooling down, because that's something that people just kind of throw out there. Well, maybe the sun's just not as hot in January, and so that's why we're chilly or whatever. No, sun, ball of death, constantly burning at the same rate. It's not heating up. It's not cooling off. None of that stuff. No, there's some other reason for this to take place, for us to be incredibly hot, even though we're farther away from the sun than at any other time, or we're cold, even though we're so close to the sun, right? It has nothing to do with distance, clearly, and it has nothing to do with the temperature of the sun, because that's a constant. What it is, the answer here, is that we are tilted. Okay, so not only do we have this axis around which we rotate, but we have this axial tilt. Okay, and this is a thing I haven't gotten into yet. You've seen it in some images in some of these lectures, and you see this again. I always go back to the globe. God, they're so cool. Have you bought one yet? Fantastic. But if you buy a globe, let's say a good, scientifically accurate globe, these things are tilted. And maybe you question it, maybe not. They just kind of look kind of sexy to have a tilt. Maybe that's why they did it. No, actually what it is they're tilted at this 23.5 degrees from perpendicular to the plane of the ecliptic, okay? Which is a fancy way of saying that our axis, it's not this perfect perpendicular relationship with that path around the sun. We're tilted 23.5 degrees from that. All right, so to go back here, this line, this plane of the ecliptic, that's our revolutionary path. That's our orbit around the sun, right? And it's a relatively flat path. That's what we call the plane. We're not like going uphill and downhill and all that. So it's this relatively flat oval that we're cruising around the sun with. And then our tilt, if we look at it in relation to that plane of the ecliptic, our North Pole is 23.5 degrees off of being a perfect 90-degree angle, right? So in some cases, I mean, and I use this term, the number 23.5 degrees. Others will say 66.5 degrees, which is this angle right here. Yeah, it just depends on what people like, what they were taught, and all that. I was always taught the 23.5, so that's why we're using it. But keep that in mind. If you're studying more stuff, going to YouTube, like whatever it is you're doing, if you see that 66.5 number, don't freak out. It means the same thing, right? We're just measuring it from a different spot there. Okay, but we have this tilt, and that tilt is constant. We're constantly at this 23.5 degrees. So throughout the year, we always have this tilt. And then what we'll see, like what this image is showing here, is that because we have this constant tilt of our axis, that's going to affect our relationship with the sun. Okay? So here we're kind of opposite of that perihelion, aphelion thing. But like here, with the, this is the Earth's position on December 22nd, which is our December solstice. Again, give or take a day. So this is close to that perihelion, right, where we're the closest to the sun, or we're closer to the sun than any other day. We should be incredibly hot, right? You would think. No, we here, at least in the northern hemisphere in California, we're experiencing cold temperatures, we're experiencing winter, and that's because the tilt is causing us to be tilted away from the sun. Again, up here in the northern hemisphere, the southern hemisphere is tilted toward it. We'll get into the opposite nature of seasons in a moment here, right? But this is why we're cold. Going back over here, June 22nd, close to that July 4th date, where we're closer to the sun than any other time throughout the year. Farther away than any other time throughout the year. Hopefully I'm not. Yeah, that's one issue when I'm just rambling in front of my computer here. Real easy to switch stuff. Hopefully I'm not doing that. And if I do, or you have any questions, send me an email if I switch stuff around and screw you up. Don't take everything I say here as gospel if something's going off in your brain, right? They're like, wait a second, didn't he just say this? But then he said that, right? Yeah. Let me know if I screw that up. So anyway, what I'm saying is we're here. If we go back here, right, this aphelion July 4th, farther away, but we're hotter, right? That's what I'm trying to say here. That's this June 22nd. That's our June solstice. You see the tilt, still that 23.5 degrees, but now we're on the other side of the sun. We're tilted toward it, or we're pointed toward the sun. That's why it's hotter. It has nothing to do with, how close we are to the sun or far away or whatever. What we're experiencing is directly connected to that tilt, right? And that's what we have, seasonal difference. Now, what I'm going to do, rather than just leave it here, is I'm going to go through 4 key moments throughout the year and make sure that you guys get how this is working. Okay, so we'll go through it. I'm going to use these images here. I like these. These are from an old textbook I use. For the most part, they're pretty good. I'll point out some issues with them, but I think this helps students figure out what's going on. And what I want you to do, my students, is, think about these 4 key dates. It's like this first one is the December solstice. I'll be talking about that. But you need to know, okay, what's happening on that day? How are we in relation to the sun on this specific day? What's pointed toward the sun? What's pointed away? Where are some of these key points that I'm showing you? Okay, and so I'll go through this one, and then we'll move on to the next day, and so on. So that's the idea. That's what we're working toward here. So on December 21st, roughly, right? Sometimes it's the 22nd or the 20th. We've already seen some different numbers on the different images here, depending on what people decided to do. So don't get too hung up on the exact date, but just know, toward the end of December, we have what's called the December solstice. Now in the northern hemisphere, we often call this the winter solstice, but I'm going to show you that's not a good name for it. Technically, it works. People know what you're talking about, but it's not winter all around the planet. Okay, so it's winter for us, but it's actually the first day of summer for the southern hemisphere. So when I say, I don't know if I pointed this out, but when I say northern hemisphere, southern hemisphere, we're talking about the equator right here in the middle. Anything north of the equator is our northern hemisphere. Anything south of the equator is our southern hemisphere. Okay, so that's what that means. And in this case, there's a real, scientific reason behind it. If you ever hear eastern or western hemisphere, we're talking about the prime meridian there. So anything west of the prime meridian is considered to be the western hemisphere. Anything east of the prime meridian is the eastern hemisphere. There's no scientific need or basis for that, because as we learned, the prime meridian, it's all make believe anyway. The Brits put it into place because they were the greatest superpower at the time. Right? That's the idea. And you find that we're not even consistent with what's considered east or west or whatever. So that's its own thing. But in here, northern hemisphere, southern hemisphere, that has a real scientific meaning. There's something natural about this division here. Whereas that eastern and western hemisphere, there's no real nature connected to it, if that makes sense. So, northern hemisphere, everything north of the equator, on this date, the December solstice, December 21st-ish, that's our first day of winter. But then at the same time, on that same day, here in the southern hemisphere, it's their first day of summer. Okay? And it's all because the North Pole is tilted or pointed away from the sun. Okay? So here's our North Pole up here, South Pole down here. We've got our tilt, and the sun is shining from this side of the image. Okay? Which you can hopefully figure out based on this illuminated day side. Okay? Now there are a few more things we need to get as we're talking about this stuff, and to understand why this is the first day of winter for us, first day of summer for those folks in the south. And one key concept is what we call the subsolar point. And so this is a location. It's an entire latitude. So we describe it as being a latitude because as the Earth is rotating, that point, it has to do with solar noon, but it's all following the same latitude. Okay? So the subsolar point is the latitude on Earth at solar noon that receives insolation perpendicular to the Earth's surface. Meaning that at solar noon, at the subsolar point, the sun is at its highest point when it's at its highest point in the sky, it's at a 90-degree angle. It is directly overhead. Okay, that's a key thing. And that doesn't happen everywhere. And if you get back to like Eratosthenes, the guy who did the whole circumference of the Earth, right, in Alexandria, that guy, he was using the subsolar point. Right, it's saying that was the subsolar point. Sun is directly overhead. It's shining into that well, right? That was the subsolar point on that day. So it's where the sun at noon is directly overhead. Okay, that's what we're dealing with here. And this only can happen in the tropics. And I'll show you what I mean by the tropics here when we get back to the Earth image. But so that means we'll never have the subsolar point here in California. We're too far north. Okay, so it's within a specific area on the planet, but it's a key thing in understanding seasonality. Okay, so again, it's this latitude where at solar noon, the sun is directly overhead. It's at that 90-degree angle. And so going back to this December solstice, on that day, the subsolar point is at the Tropic of Capricorn. Okay? And anytime, here's just a little study tip from me to you. Anytime someone took the time to name, like to give a unique name to a specific line of latitude or longitude, It's important, right? There's a reason for that. We don't just randomly name these things. There's some basis for it. It means something. So it's good to, as you're studying, like if you see something like this, study, not only what is that line of latitude or longitude, but also why do we care? What's important about it, right? So in this case, the Tropic of Capricorn, this line right here, it's 23.5 degrees south. And of course, we've seen that number before, right? It's not a coincidence. It's directly connected to our tilt itself, right? But this 23.5 degrees south, it's the furthest south the subsolar point will be throughout the year. Okay? So because of that, on this day, the southern hemisphere, everything south of the equator, is going to have their longest day of the year. Right? And in the northern hemisphere, because that subsolar point is so far south, we actually experience our shortest day of the year, which connects with, again, the first day technically of winter, first day technically of summer, longest day, shortest day, like it's all connected, right? That's the idea here. Okay? And what this is showing, this dividing between day and night, we call this the circle of illumination, which sounds hilariously weird. It sounds like some cult thing, like something people in robes would be talking about. But the circle of illumination means that there's one half of the earth that is illuminated, that is lit up by the sun, right? And so we rotate in and out of that circle of illumination, right? That's why we have day, that's why we have night. So it looks like the sun is rising. The sun's not doing anything. The sun's in place, right? We are rotating into that circle of illumination. That's what sunrise is. And then sunset is us rotating out of that circle of illumination, right? That's the idea. But what we have going on with this is that we're rotating in and out here, and because of the tilt, this is what's affecting those short days and those long days. Okay? It's the tilt itself. Again, the tilt is the key thing here. So we got some crazy stuff going on. And I should point out too, this word solstice, I forget the exact Latin or Greek definition, but it means an extreme day, right? The day is doing something crazy and extreme, more so than any other time throughout the year. Okay, so that's what the term means. So what we have, like I said, these longest, shortest days, all this stuff, we've got some crazy stuff taking place. And it's more than just having your longest day or whatever. Like right here, we have the Arctic Circle, which is at 66.5 degrees north. And again, not a coincidence, connected to the tilt. And again, whenever we, label something, it means something. So make sure you're studying that. Make sure you understand it. But on this date, on this December solstice, at the Arctic Circle, they have a full 24 hours of night. All right, meaning that they're never going to actually rotate in to that circle of illumination on that specific day. Right? So they're right here. They're rotating, but it's all happening outside of the circle of illumination. All right. Now the next day, so if like on this year, the December solstice takes place on December 21st. On December 22nd, they're going to get just a little bit of sun. They're going to move, and we'll see how this changes throughout the time. But what they'll do is they'll get just a little peak of sunlight, but it won't be that full 24 hours of night. All right. So it's just on this one day, it's a full 24 hours of darkness, which is pretty amazing to think about. And then what's crazy too, and I don't have it written here, but the further north you go, because again, this is 66.5 degrees north, but what's the latitude of the North Pole? Perfect. You remember, 90 degrees north. I assume you remember, whatever. Make sure you're taking notes. With this, as you go further up, you're going to have longer periods of darkness. And by the time you get to the North Pole itself, on this date, on the December solstice, it's the first day of 3 months of complete darkness, of never moving in to that circle of illumination, right? Never seeing the sun for a full 3 months. It sounds miserable. But, people live not at the North Pole itself, but up in these, in the Arctic, people deal with it. In fact, if you really want to get a sense of what it's like, there's a very scientific movie that was made years ago now. It's a classic at this point, and it's called 30 Days of Night. Very scientific. I encourage you to watch it. Everything in it is true. Except for the vampires that slaughter the Alaskans. Spoiler alert. Okay. I don't think vampires are real. I don't think. It's a pretty good movie. But it's the idea, that whole idea of one town in Alaska where they have 30 days of night, right? A month of darkness. It's because of their location, above the Arctic Circle. That's what's going on there. So that's what's happening up here in the Arctic. And then for the rest of us, it's like this is showing 40 degrees north. We are, roughly 34 degrees north here in the, greater Los Angeles area. About the same thing. We make it into the circle of illumination. So we do see the sun, but because of that tilt, we're only in the circle of illumination for a short time compared to the rest of the year. So we have our shortest day, whatever that might be, right? And it all depends on latitude. Maybe your day is 6 hours long, maybe it's 8 hours long, but it's going to be less than 12 hours, okay? And then down at the equator, which is at the perfect midpoint between the North Pole and the South Pole, they're going to have a 12-hour day, 12-hour night. And what we'll see is at the equator, they constantly have 12 hours a day, 12 hours a night, because they're right there in the middle. Okay, so that's a constant thing down there. And we'll get into what that means later on. We get into climate stuff. And then further south, we get to the Tropic of Capricorn, where we have, that's the subsolar point. That's why we're having this longest day of the year. It's going to be greater than 12 hours, right? Anywhere between, 12 hours, 1 minute to 23 hours, 59 minutes or whatever in this area right here. And then at the Arctic Circle, they're going to have 24 hours of day. So you can see they never actually rotate out of that circle of illumination, right? So they're just rotating, spinning around here. The sun never actually sets, nor does it really, rise in that sense, because they're just there. They're seeing it. And then at the South Pole itself at 90 degrees south, it's the first day of 3 months of the sun always being up, of never having night, right? Again, sounds awful, but that's how it works. Okay, and so that's what this whole December solstice is all about, right? It's this extreme day event, and that means, again, for us, it's our first day of winter. It's a definite shift in the seasons for us, and it's the first day of summer for those folks in the south. Definite shift for them as well, right? The only people who don't really see a shift ever are at the equator, okay? And the tropics in general, which is between technically the Tropic of Capricorn and the Tropic of Cancer, which we'll see just 23.5 degrees north. That little band in the middle of the Earth, not a lot of seasonal fluctuations there. It's kind of like summer all the time. It's always hot throughout the year, right? Some exceptions here and there. And again, we'll get into that with climate down the road. But for the rest of us, like in the mid-latitudes, we have these definite seasonal fluctuations, and it's that tilt, okay? So again, as I was saying, with these, as you're studying this stuff, I want you to be comfortable with, like, just knowing what's happening on the December solstice. So if I ask you a question like, where's the subsolar point on the December solstice? You go, December solstice, first day of summer for the southern hemisphere. It's got to be the Tropic of Capricorn, right? 23.5 degrees south. You got it. You understand it. Fantastic. But I can also ask you, the subsolar point is at the Tropic of Capricorn. What day is it? You should go, okay, that's 23.5 degrees south. So if the subsolar point's there, it's got to be the December solstice, right? Just be able to know the stuff and be able to work back and forth with it. Because these exact dates, they're important as we move on, as we get into climate, which is very important when it comes to life on this planet. It's important. It's good to know what's happening on these days. All right? So hopefully that makes sense. Now, let's move past the December solstice, and we're going to get to March 21st. Again, roughly. Give me the 20th. Give me the 22nd. This is our March equinox. It's also called the spring equinox or vernal equinox. Again, these are bad terms because it's spring for us, sure, but it's not the case for those folks in the southern hemisphere. So this is why we want to get out of that habit of calling it by the season that we experience, because we're ignoring the fact that it's not the case. That's not a universal thing, right? So March equinox, and equa, think equal. What an equinox means is we have an equal day and night everywhere on the planet. The North Pole and South Pole gets kind of funky up there, where they're starting 3 months of, it kind of feels like dusk or dawn, like sunset or sunrise, depending on whether you're coming out of 3 months of darkness or 3 months of sunshine and all that. But for the rest of us, 12 hours a day, 12 hours of night. Okay? And what that is, it's because the subsolar point is at the equator. Okay, so it's at 0 degrees. It's hitting, the subsolar point is hitting the Earth right there in the middle. That's what leads to this 12 hours of day, 12 hours of night. But what's the issue here? When you look at this image, how is this different from the one we just saw? You guys see that? Let's go back here. Look at that. What's different there? What's going on? It's my tilt. Where'd my tilt go? What happened here? Does our tilt, did it just go away? Did it just decide it was tired of tilting and wanted to straighten up, fix itself in that way or something like that? No, tilt is still there. That tilt is constant. And this is one of the issues I have with these images, is it makes it look like the tilt goes away. And it would be easy for me to show this were we in the classroom and I have my globe and I'm doing props and all that stuff. But what you need to envision here, that tilt is still there, but the tilt is not affecting the Earth and the sun. Okay, it's as we move around. So if we go here, let me put it this way. In fact, let me go back here. This is what we'll do. This is how we'll make it work. We'll look at this thing, right? So we just had our December solstice that we were talking about. North Pole tilted away. Okay, now we're continuing to revolve around the sun. Remember, so we're doing our calendar year. We're cruising around the thing. This is showing that direction. So we would be, as we're going into March here, we'd be on this side of the sun. Now the tilt, it's still the same angle, right? As we have here and we have here. It's still oriented in the same way. So it's still at 23.5 degrees. It's still pointing more or less to this corner of the screen up here. But when we're over here, yeah, we're tilted, but we're on this side of the sun, so the tilt doesn't matter, right? The sun's rays are coming this way. Our tilt has us leaning this way, so it doesn't matter, right? The sun's rays hit us perpendicularly at the equator right here. And that may be kind of weird and abstract. I know it makes sense in my brain because I'm the one doing this stuff, but you watching just the, this little red thing move around, that might not help. But the idea that I'm trying to convey here is that tilt is still happening, but the tilt, and the way this should be drawn, it should be tilted in a way that the North Pole is like here, right? And the South Pole, it would be kind of tilted away here. This is actually wrong. How they've shown this North Pole and South Pole in this way. It's tilted, but the sun's rays are coming in from a different angle, so that tilt doesn't matter. And that's why the subsolar point is at the equator. It's why we experience these 12-hour days, 12-hour nights. And so for us, if it's spring, for us, we're leaving winter, right, here in California. Say we'll use us as the example. So it's cold in the winter. And as we get to this March equinox, we're starting to warm up because our days are getting longer. So that's why, we love spring, right? Because it's starting to warm up, but it's not that god awful summer heat. So the weather's just nice. It's just a nice thing. That's what spring is. It's our days are getting longer, but not as long as they're going to get in the summer, which is what we'll see when we get to June here, right? So that's what spring is for us. At the same time, down in the southern hemisphere, they're leaving summer and they're technically entering fall right here. Now they're experiencing the same days we are. It's really a matter of perspective. You're leaving your hot summer, right, and getting into cooler temperatures because your day is shortening, right? So that's what fall is. Fall and spring are effectively, it's the same thing. Our day length is about the same, but we have different stuff happening. We're experiencing it differently just because of our perception. And plants and animals are doing different stuff because of chemical reaction things that are induced by the temperature change and all that. We'll talk about some of that down the road when we get to that. But honestly, with an equinox, everybody's experiencing the same thing on that day. Right? That's what that means. It's equal. Equinox. Keep that in mind. All right, so that's that. Now we continue on through our year. June 21st ish. Our June solstice. This is the exact opposite of that December solstice. So now our subsolar point is at the Tropic of Cancer. And it's because that tilt hasn't changed. But now with the tilt, we are leaning toward the sun. So 23.5 degrees north is our subsolar point. We experience our longest day of the year. The southern hemisphere folks experience their shortest. It's our first day of summer, their first day of winter, all that stuff. It's the opposite here, right? And same thing, like 24 hours a day at the Arctic Circle, 24 hours of night at the Antarctic Circle. So just, everything we learned about with the December solstice, it's the opposite is taking place, right? So just switch a lot of that stuff. And it's because that subsolar point is at the Tropic of Cancer, the northernmost subsolar point we'll see throughout the year. All right, and then we continue on. September 21st, our September equinox. The subsolar point is back at the equator. And so it's the same thing with the March equinox. We're just on the other side of the sun. And the tilt isn't affecting our relationship to the solar radiation. So the subsolar points at the equator, equal days, equal nights everywhere. And so we experience, fall for us because we're leaving summer, spring for those folks in the southern hemisphere because they're leaving winter. You follow? Pretty straightforward and simple, right? And we're not fully there. There are a few more things I gotta point out. But this is what's happening. This is our relationship between the sun and the earth throughout the year. Okay? And this gets into why we experience the weather, therefore the climates that we do experience. And if this is still kind of fuzzy, if you're having a hard time grasping this, I do have this in the actual Google slides. I have this one YouTube video embedded in there, so you can watch that. See this stuff actually animated. There are all sorts of resources out there. Feel free to watch this or search for other stuff to help it click in your brain. Because I know when I was initially learning this stuff, seeing visual things, well, that helps me with a lot of this stuff. So, go out, use this, or go out and seek some other stuff. But that'll hopefully help. Now, another thing to get into is that we got a few more things to kind of wrap up here. So it fully clicks and you get all the connections here. We got this thing here to start with, the analemma, which is this weird figure eight, kind of dumpy figure eight looking thing, lopsided looking deal. And this is a model right here. But what it's showing is what the sun is doing, what the subsolar point is doing, how it's moving throughout the year. So to read this, and don't worry, like in this, you're not going to have this image on your test or whatever, but to read it, we've got the days of the year, right? So you can see May, June, July, August, and it's showing us, based on that date, where that subsolar point is. So, I'm recording this mid-June right now. We are approaching our June solstice, and that means the subsolar point, it's not quite at the Tropic of Cancer yet, but it's really close. It's like at 23 degrees north right now. But on that date, I don't even know what it is this year, if it's the 20th, 21st, or whatever, but that subsolar point will be at 23.5 degrees north, right? And as the summer progresses, the subsolar point will drop down, and eventually we'll get down here to where it's at the equator, and that's our first day of fall, and blah, 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 right? That's how it works. And so we've measured this stuff. This is kind of cool to look at, but what's even better is not this drawing, but to really see what the sun is doing, right? And you too can do this if, say, you have a camera and a tripod and a year with nothing going on, which actually, this would have been a good COVID project now that I think about it, because what else are we doing? But what this is a series of photographs that were taken and then, overlaid on top of one another. So this is showing what the sun is doing at this specific location throughout the year. I stole this off of Google. I have no actual, metadata about where it was taken and whatever. I'm going to assume it's a Russian thing, just based on the name right here. Even though that could be totally wrong. I don't know. But we can just assume this is the northern hemisphere. And, what we could say it's at noon, right? To keep it simple and straightforward. So if we're looking, we've got this analemma right here. All right, and so what we're looking at is seeing how the subsolar point, how that movement of the subsolar point affects where the sun is in the sky, or what we call the solar altitude. Okay, and this solar altitude is just that angle between the horizon and where the sun is, up in the sky itself. Okay, and so with this here, if you're looking at it, you got to get a sense of the time of the year, right? Like if at this one, the highest point in which we see the sun, what season is that we're dealing with? Summer, right? So that should be, I don't know again exactly, but we can just assume this highest point right there, that was taken on the summer solstice, right? And this is not the subsolar point. So if it is noon, it's not directly overhead. It's out of that 90-degree angle, but it is definitely higher in the sky than at any other time throughout the year, right? Whereas this lowest one down here, that's going to be the winter solstice, right? Or the December solstice, if we're again in the northern hemisphere, assuming that, where the subsolar point is the furthest south throughout the year, and therefore at noon on the day in this specific location, the sun is barely peeking over the horizon. All right, because the sun's effectively down on the other side of the globe, if you want to think of it that way. And so the solar altitude that's going on, that angle at which the sun is up in the sky, that's going to affect what we experience. All right, here's some other images I stole, because I ain't got time, to stand out and take pictures of the sun and all that, but luckily other nerds do. I take my own nerdy pictures of other stuff. They can use them. I'll steal these things. But so what this is showing, December 21st, at the December solstice, again, clearly based on where the sun is, this is in the northern hemisphere. So the sun at its maximum altitude at solar noon, it's at 22.1 degrees. It's barely peeking over this building right here, right? But moving forward, right? So this is 2014, this is 2015, June 18th. So roughly around that June solstice, that first day of summer. Sun's maximum altitude, 68.9 degrees. So much higher up in the sky, right? And so based on that, we're going to be dealing with the sun for a much longer period of time, right? Think about the time it takes from it to rise and get up to its highest point and then set. We're just going to have longer days, right? By default. Like that's what we got into with this whole solstice stuff. So because we have these longer days, we're exposed to the sun for a much longer time. Whereas down here, it's going to peak up, get up here, and quickly go down. We're going to have this very short day. So we get more insolation on these longer days than we have shorter days, right? That just makes sense. But there's another key thing too, and it has to do with this altitude. It's not just the amount of time we spend with the sun, but that angle directly reflects the direct or indirect amount of solar radiation we're getting. And this affects the Earth in two different ways. Number one, it affects it from this global standpoint, where latitude is going to determine just how hot or cold your days are going to be. Down at the equator, so these columns here, it's the idea if the sun is shining, what this is showing, because the sun's so massive in our relationship to it, the sun's rays are all coming to the planet from that same angle, right? But they hit the equator more or less at a perfect 90-degree angle throughout the year, right? If the subsolar point isn't at the equator, on those 2 days, it's pretty close tonight. You're getting it at like 88 degrees rather than 90 degrees or whatever. So you're getting this direct bombardment of insolation. As you move up, because of the curvature of our round-ish, right, our geoidal planet, that those rays that are coming in, they hit the Earth at this oblique angle, and therefore they spread out. It diffuses that solar radiation, and so the further up you get on this curve, the more that radiation is spread out, meaning you get less of it in a specific location, say up here in the Arctic, than you would down here at the equator. That's why it's always hot down here, and we have a very distinct climate. That's why we have ice for the most part, every day of the year up here. It also helps to explain like why you can have a place. Like I just got done explaining how, at the North Pole, you have 3 months of day, right? The sun is shining constantly, 24 hours a day for 3 full months, right? Yet it's still covered in ice. And that's because, yeah, you see the sun, but it's hitting at such a weak angle that sunlight is, or that, the actual energy is spread out over a massive area. So it's still freezing, even though you see the sun. And again, it's all connected to that solar altitude, where it is. If I go back here, when this is hitting us, right, it's coming in at that low angle, so it means those rays are going to hit at the weird angle and spread out. It's going to be colder. Whereas up here, it's higher in the sky. It's going to hit us at a more direct angle, and so that insolation is going to be concentrated. It's going to be hot. So that's why we experience hot temperatures, cold temperatures, right? And finally, to help explain that, I've always liked this analogy here. This came from another textbook, but using the flashlight, kind of get a sense of what the angle is doing. So this 90-degree angle, holding that flashlight directly overhead, that's like the subsolar point, right? So it's shining down at that direct angle. That's this whole bit of energy is covering 1 unit of surface area. Kind of a generic thing, but just go with it. It'll be relative to this other stuff. If we tilt this flashlight at a 45-degree angle, same energy. If we're thinking about this as insolation and not just a flashlight, right? Same energy, but now it's spread over 1.4 units of surface area. And we bring it down to 30 degrees, same energy, 2 units of surface area. Or another way to think about it, you're getting half the energy that you would if the sun were like this, right? So this explains, like with winter and summer, the differences that we experience here, say in the Antelope Valley in Southern California, we'll never have the flashlight like this, right? The sun is never at that 90-degree angle, but in the summer, like what we're feeling right now, again, I'm talking about this, during June, a few days before the June solstice, the sun is going to be at its highest point, and you just feel it beating down on you, right? And that's because we're getting a more direct concentration of insolation. But if we move forward throughout the year, we get to December, that sun is going to be lower in the sky, same amount of energy, right? Remember, it's still burning at the same rate, but in this case, it's going to be spread out over, let's say, twice the area. Therefore, we're getting half of that energy, it's going to be colder. Even if the sun comes up, it's not going to feel the same way as it does right now in June, right? So that's how this solar altitude is important to what we're experiencing. But again, that solar altitude, it's all connected to the tilt of the Earth. Is that making sense? Hopefully it's clicking. Again, YouTube is your friend. Read through this stuff. I want you to make sure you grasp this concept. Well, that was fun. And you know what? You know what's really exciting? You know what's going to be great? Yay! Test day. Now in here it says, don't forget your Scantron. We ain't got no classroom, right? So ignore that. Really, what you need to not forget is to log into Canvas. And I believe, technically, it's like I forget exactly. Check Canvas. But one of these days, coming up at midnight, the test is going to open up. Right, I've given you, I think you've got like 5 days from when it opens to when it's due. Right, so just make sure, don't, my God, as soon as it opens, don't get excited and rush into it and be like, I just want to get it done and try to be done with it. No, pause after listening to this and all the lectures, go through your notes, read through, work on that homework you have due. That's coming up. Don't forget about that. Slowly go through the stuff. Get to the point. Use that study guide. Use the township and range. All this stuff. Use the time to just kind of go through, get comfortable with the information, and then when you're ready, and when you have a stable environment, right? When you get 90 minutes to take the test. And what that means is as soon as you hit start or begin or whatever it says on Canvas, 90 minutes starts counting there. So you can't start and go oh, I forgot I got to run to do this or, do whatever. No, you're out of luck with that point. All right. So as soon as you hit begin, you're locked in. So make sure you have 90 minutes to sit quietly in a room or wherever and be able to complete this, right? From start to finish, because it will be timed. And once you click out of it, shut down the computer, you can't get back in, right? Or once you hit submit quiz or whatever it says, you're not going to be able to get back in. So make sure you dedicate that time. And it's a case where I got to say, zero excuses, zero tolerance. That's just how it's going to be. It's up to you to make sure you can make this work. That also means you have to have a stable internet connection and all of that stuff, right? Because I can't just handle the different excuses that show up and this and that. I'm not going in to try to set up a new test for you or whatever. No. You start, you end, just like we would be doing if we were in a classroom. Okay? So keep that time in mind. And as I've said before, I fully understand. We're not in a classroom, so therefore, by default, it's open book, right? Because I can't watch you on this stuff. But also be aware that doesn't necessarily work in your favor as you're going through. Google doesn't always give you the right answers for this stuff. And as you're trying to figure some of this stuff out, time is just going to be taken away. So go through, organize your notes. Make sure you have a general idea of what this stuff is. Sure, you can still refer back to your notes. It's easy for you in that regard, but you gotta know the stuff before you start it. And also, my final note here, as you open it up, you should see everything in there, all of the different questions that are there. You can answer them in any order you want, right? At the bottom of the test, the last 2 questions, as I discussed, are going to be that finding your latitude and longitude. So I'm going to give you a word problem, effectively 2 word problems, give you all the information you need, and then from there you figure out, okay, I'm at this latitude, I'm at this longitude, right? You might want to do that first, since that's going to take more, calculations. You actually have to write stuff out, and then move on to the different true, false, and multiple choice things that you'll see, right? Because that way, at least if you're starting to run out of time, and you can just do kind of a Hail Mary and just click stuff and hope you get some stuff right. You follow? So you strategize with this stuff. That's the key. That's how you're going to do well. Strategize and do the best you can, and best of luck. So as I said, that test is going to open up relatively soon from when you're listening to this, and so be aware of that. Be ready to go, and best of luck. And of course, as always, any questions on any of this stuff, the test itself, stuff on the study guide, like whatever, let me know. Talk to me. Communicate with me. However you want to, we'll figure that out, and you guys will be set. And then once we're all done with exam 1, we're going to forget about all this stuff. We're going to move on to some other things, right? So we'll kind of start fresh. And sure, we'll build up on some of this, like this insulation stuff I talked about, but it's all going to be new material, right? So we just want to get through this so we can move on to the next phase of this class. You dig? All right, geographers, happy studying. Enjoy. Good luck on the exam if I don't talk to you before then. Yeah, I'll talk to you later.